Hello. Good evening. Ladies and gentlemen, it's my great pleasure to welcome you to this lecture given by Professor Blanford from Stanford University. So my name is Shuang Zhang. I'm the head of Department of Physics at the University of Hong Kong. So Professor Roger Blanford has made a groundbreaking contribution to the field of astrophysics, in particular for his theories to explain the formation of the relativistic jets of black holes and how the jets extract energy from the rotation of the black holes. Professor Blanford also made significant contributions to the study of astrophysical particle acceleration and gravitational lensing. Professor Blanford has been recognized with numerous awards and honors, including the prestigious Crawford Prize in 2016 and the Shaw Prize in 2020. He's a fellow of the Royal Society and a member of the US National Academy of Sciences and the National Academy of Arts and Sciences. So today, he will be presenting a very interesting topic that's sure to expand our understanding about the universe. And the title is Active Social Lives of Black Holes. So now, please join me in welcoming Professor Roger Blanford.
Well, thank you very much, Sean. Thank you very much. Kenneth Young and all the people here from the Shaw Foundation. Thank you very much, Jane Dye, for the invitation to come here to Hong Kong. And I would also like to acknowledge the memory of Sir Ramanan Shaw. I'm honoured and humbled by the award of the 2020 Shaw Prize, and so glad also to be here to attend a meeting on this topic of black holes. And many friends and colleagues from around the world have been joining us here, and we've had an exciting 2 days, and we have 2 more days we're looking forward to very much indeed. Okay. I warned I was not good with microphones, so is that better? Okay, thank you. All right. Okay, so what I want to do in this talk is persuade you that black holes are common and very real, and they're a large part of the universe. And they're not the fearful monsters that have been associated with, but instead have a much more benevolent effect on their environment. And I'm going to, in some jocular way, try and persuade you you can humanize them, and they have a very active social life. So what I'm going to do now is give you where, in some sense, many of you may have started from, is that black holes now have become very famous. They have been associated with some widely publicized and genuine discoveries, and here we have 3 of them. The first was the discovery, the direct detection of gravitational radiation from merging black holes, and that was in 2015. The second here is an image of the shadow caused by a black hole in the center of a nearby galaxy called M87. And the third is a picture of the orbits of stars that have been traced around the black hole at the center of our galaxy, the Milky Way, and that all of these have had a lot of publicity, and 2 of them, of course, have won Nobel Prizes, but there's much more been going on, and one of them is these black holes are associated with the extremes of astrophysics, the very highest energy photons called gamma rays, the very highest energy neutrinos, ghostly particles that you may have heard of, and then finally the very highest energy cosmic rays that we observe on the Earth. And I'm going to try and tell you about all of these topics in this 1-hour talk. Now, the ideas that the black holes are real and so on, these were big discoveries, and perhaps the one that got the most publicity was the one made by the Event Horizon Telescope, and many of my colleagues here worked hard for many years on making this project work. But it wasn't, everybody didn't quite believe it. One of my colleagues who is here, when I first saw the image, I sent it to her, and this is what she said: it's all a hoax. You may have noticed that although black holes may be black, everything around them is orange. You may have seen that. You'll see that again. And then here's a joke, I suppose. And there are more of them. Anybody looking for a new career, scientific cartooning, it's a good place. There's plenty of room to improve on this. Okay. Some of the lamest cartoons around. Now, black holes have inspired a lot in popular culture. They've entered it internationally as agents of doom and destruction, staples of what I can only call to be pulp fiction, and the true casualty here may actually be the narrative. But so there's a lot of attention being paid in popular culture to black holes. They've been seen as allegories of hell in a religious connotation. This is, of course, Botticelli's reworking of Dante's Inferno, and it looks rather like a cartoon of what's going on around a black hole. And if your interests are less spiritual and more financial, as a few people are in Hong Kong. I'm sorry, they're US, not Hong Kong dollars, but nonetheless, the metaphor works just the same with Hong Kong dollars if you disapprove of public expenditure, and economists and politicians are very fond in invoking black holes as not politely. And then there are the movies. There are several that have been inspired by black holes. Here are two of them. And here the destruction has probably been to the careers of several otherwise promising movie stars. The first one on the left-hand side introduced some impressionistic stabs at the science of gravity, of gravity, and they introduced gravity-free zones, an evil genius, mechanical vices, extrasensory perception, and Anthony Perkins. The heroes went over the event horizon of the black hole, and then somehow or other there was a happy ending. The second was quite explicit about the idea of an event horizon, which we'll say a bit more, you probably know this, it's an imaginary surface that surrounds the black hole, a point of no return from which light, matter, and not even superheroes can escape. It invoked white holes, which are time-reversed black holes. They were there. The incipient violence of black holes was mediated by the actors who seemed to wander off into a slasher movie. The critics were not kind. Neither, I should emphasize, was made by Sir Run Shaw. By now, you're probably thinking that black holes are a very bad thing. And my task here, I suppose, is to persuade you that it's not that bad. They really do exist, and they perform lively and vital roles in the cosmos. And they're also teaching us a lot about basic physics. And even more discovery is on the way. So a few more movies, a couple more. One is one that was much better. It was by Carl Sagan, and my colleague Kip Thorne and a student of mine were actually advisors to this. And this was much more creative. It depicted radio astronomy with some license, but not too much, and explored some very interesting ideas, including wormholes, which are generalizations of black holes, as I mentioned, that in principle allow time travel. In this movie, a sort of interstellar metro station might be invoked, and you may be saying this might be a good way to get out of your current predicament, but my own view is that wormholes do not and cannot happen at the macroscopic level, but I can't prove it. So wormholes are certainly one of science's great gifts to Hollywood screenwriters. So when they've written themselves into a corner, they can invoke a wormhole and to go on to another movie. So at any rate, so I would say if anybody tries to sell you a wormhole, don't bet on it. Okay. My colleague I mentioned, Kip Thorne, he actually went on to an even more famous movie, a more recent movie called Interstellar, which went through many, many transformations. It emerged, what emerged essentially was a physics, from a physics perspective, was a dizzying array of pedagogic demonstrations of weird physics that is widely accepted. One of them was differential aging. If you're in a gravitational field, you will age at a different rate. So this is a father-daughter relationship in this movie. Go figure. There were many serious ideas being explored here in a rather exaggerated way, including a space with more dimensions and notions, which I think the kind of thing that I can say is it's a work in progress as far as physics is concerned. There were some wonderful graphics, and there was a story. So my colleague Kip Thorne had to write a book about this to explain the physics to the rest of us, and that's worth reading too, as well as seeing the movie. I actually really liked it, but at the time I had a sort of vicarious relationship to it, because I too was writing a book with Kip Thorne. It was called Modern Classical Physics. It has got 1,600 pages and 3,000 equations. It's a textbook for graduate students. So, but Kip, I have to say, he's generously and graciously signed over the movie rights to me. I'm still looking for a top-name director. At any rate, to science. Let's start talking about gravity. I want to start with Isaac Newton and Woolsthorpe Manor, which was where he was born. You can tell that, actually, because those of you who know some calculus will see the integral signs, as well as the apple. That is a cruel joke, because his bitter rival Leibniz invented the integral sign. But nonetheless, this is really what it looks like. I know because I was born 5 miles away from here, and I boast about this to my students, and they are totally unimpressed. You know about the story of the fall of the apple, and which almost certainly is just a myth, but it was the real science behind it. The moon and here and rockets, of course, follow the same law of gravity and the same laws of motion as the apple falling to the earth. And it was Newton's genius to be able to recognize this and put it in the language of mathematics, and in fact solving the equations which he derived so magnificently and developed so magnificently was the foundation of most of physics until the quantum era, when quantum mechanics came along, and that's sort of one way very much of looking at gravity. Now, there's Leibniz, and here are some equations. Some of the physicists here in the audience may have seen, the students may have seen F equals ma, and the new law of gravitation and so on. And these are the equations that were the foundation, as I say, of a lot of physics and the generalization, the reworking of them in many different ways. Jumping forward to 1905, Albert Einstein, seen here as a young man, he introduced his special theory of relativity, and in this space and time were in some sense unified into a four-dimensional structure called space-time, and they were not separate and absolute, and there was that's why it's called relativity, and there were various consequences that it basically follow from what was then a conjecture and something we know to be extremely well tested, that the speed of light is constant and as measured by anybody in any place and time. And so this means that if you go off on a long trip, you will age less rapidly than your twin, for example, staying here on Earth. So if somebody goes on a rocket ship and then comes back again, you have aged less rapidly. So there are many, many consequences, and there really is absolutely no doubt about this because there are physicists all around the world in different places validate this on a routine and regular basis. And also associated with this is what is said to be the most famous equation in physics, E equals mc squared, which is associating energy with energy there, with matter, with the amount of matter. And this, of course, is firstly very important in nuclear physics for understanding how you get nuclear power in a nuclear reactor, but it's also very important in the context of general relativity, which I'll come to next. And this is will be even more important in the context of gravity. So in 1915, after 10 years of extremely hard thinking and many wrong turns, Albert Einstein came upon his general theory of relativity. And this was a magnificent generalization of the theory of special relativity, which did not have anything to say about gravity, and he knew that gravity ought to be part of the story. And so his way of doing this was to say that space-time, this four-dimensional structure, this union of space and time, was curved. And that curvature of space-time told matter, like the apple or the rocket or the moon, it told it where to go. And it essentially followed a straight line in space-time, the generalization, if you like, of a straight line. But the other side of this theory was the curvature itself was created by the amount of matter and or energy there. And this is embodied in Einstein's equation, written in a rather oversimplified way here as G equals 8 pi, you heard of the constant pi, times T. And G stands for the curvature, so it's just a measure of the amount of curvature of space-time, and T is all the stuff that's there. It may just be stuff like you and I, it may be radiation, it may be other more exotic things, and that's there on the right-hand side of this equation. And this is Einstein's theory of general relativity. So everyone here can go home and say, I have studied relativity, I understand it, G equals 8 pi T. Any questions? You too. Okay, so let's go on to black holes. Within a year of the publication of the general theory of relativity, a German soldier, remember this is in the middle of the First World War, a German soldier called Karl Schwarzschild, who was also an observatory director, but a fine physicist and mathematician as well, he discovered a solution to the equation that I just wrote down, and today we know, what he didn't know at the time, was that it describes a black hole. It describes a rather special type of black hole. It is one that is spherical. It looks the same from all directions. So it's a spherical black hole. He wasn't the first person to think about this. There were earlier scientists, most famously an Englishman called John Mitchell, shown here on the left-hand side, and he too had wondered about black holes. And he said, what would happen if I had a certain something like the sun, and it was squashed so close together that not even light could escape it. Light wouldn't have what we call the escape velocity, which is the velocity we'd have to, if a rocket to leave the Earth, we'd say that's the escape velocity. What happens if we had something so squashed that not even light could get out? And he sort of speculated about this, as do one or two other people, but it was Schwarzschild who put it onto a firm mathematical foundation by solving Einstein's equations. And this describes a black hole with a solution that bears his name, and this has an event horizon, which is this surface which I'd introduced, and I think everybody has probably heard of. It's a sort of imaginary surface around the black hole from which, if you cross over that, and it's a sort of big black hole, then you cannot escape. There's no way back. So we would say, on the basis of this, wearing our mathematical hats, that black holes can exist. Let me go forward in this history to talk about stars. Not the regular stars like the sun, but here are two special ones. The first one on the left-hand side is called a white dwarf. It's small. It's about the size of a planet, a regular planet. Depends on what the mass is, but it's roughly about the size of the Earth, say. And then the one on the right-hand side is called a neutron star, which is much smaller. It's about the size of a city, like Hong Kong, for example. So it's about 10 kilometers in radius. And it is very dense. In fact, it's like a giant atomic nucleus. It has the density of an atomic nucleus. And here on the right-hand side of this picture are two people who, Subramanian Chandrasekhar and J. Robert Oppenheimer, who recognized, firstly, for the white dwarf, Chandrasekhar, that there was a maximum mass that you could have for this white dwarf. And if you piled more and more mass on top of it, it would have to collapse. Oppenheimer made the similar argument, but in the context of relativity, for a neutron star. There was a maximum mass of the neutron star. And in both cases, the maximum mass is a few times the mass of the sun. And we know that there are stars out there with hundreds of times the mass of the sun, so they have a problem. Now, many physicists were very resistant to this idea because it's a problem they didn't want to confront because it had important implications, which I'll come to in a moment. But nonetheless, they essentially, when you took their astrophysical insights and combined them with astronomy and what we knew of what was known about stars at the time, you could conclude that not only that black holes can exist, but they really must exist from an astronomical perspective. If we then forward to the 1960s, here are four of the many highly talented mathematical physicists. I've just picked these four, but there are many other people I could have done, who contributed to our understanding of black holes in the same spirit of Carl Schwarzschild in 1916. On the top left is Roy Kerr, who found a solution like Schwarzschild, but this time for a black hole that was spinning. And it was a remarkable tour de force mathematically. On the bottom left is John Wheeler, who popularized, he wasn't actually the first to use the expression, but he popularized the phrase black hole, and he had a large group of students, he founded essentially a school, who thought through the physics of black holes and neutron stars. On the top right is Roger Penrose, who produced some of the mathematics that was enable us to understand that when you have a black hole forming, it was inevitable that you would get to a point inside that black hole, a point in space-time, if you like, called a singularity, when things would get worse and worse and worse. The forces that you're exposed to would get larger and larger and larger without limit. In some sense, the ability of regular physics to calculate or predict what would happen next is reached. You cannot go beyond that. People don't know what to do beyond that. The solutions assuredly involve quantum mechanics, but in a way that is still an unsolved problem, and we do not know how to describe with it. And the challenge of dealing with this singularity, which Roger Penrose was one of the first people to show had to exist, was something that made people think, well, nature will save us from this embarrassment and black holes won't form. And then on the bottom right is somebody who's probably the most famous of all of them, is Stephen Hawking, who contributed some important mathematical theorems about black holes, and one of them I'll come to in a moment, which is essentially central to one of the things I want to say. So the black holes that were described initially by Roy Kerr are not just, like Schwarzschild's black holes, characterized by one number, which is the mass, but there's a second number, which is the amount of spin that they have. So a black hole of Kerr's type is essentially just two numbers. That's all you need to describe it. It's a very simple thing. It's simpler than an electron. It is true that you can get generalizations of this that have charge and go to different dimensions and all the rest of it. But as far as astrophysics is concerned, you are really only concerned with the black holes of Roy Kerr, which are described by mass and by their mass and their spin. And that's all. Those are the two features they have of it. In that sense, they're simpler than even an electron, which requires three numbers to characterize it. So they are very simple. And these are the stage. This is the stage, if you like, on which great cosmic dramas are enacted and observed by astronomers. So let me say a bit about black holes and how they are seen. They can release energy. Now, one way of releasing energy is just dropping something on the floor. If I just put something on the floor like that, there's some gravitational energy that's released, and whatever I dropped will have gotten a little bit hotter. The energy would be conserved, and so it got a little bit hotter. If we do that around a black hole, we drop it an awful long way, and it gets an awful lot hotter, and so we release an awful lot of energy, typically a good fraction of the E equals mc squared energy that we talked about. And the way that this is done most commonly in astrophysics and in the universe is through a ring or a disk of orbiting gas called an accretion disk. A little bit like Saturn's rings, but obviously with a much smaller black hole at the center rather than Saturn, and the gas is orbiting around there, spiraling inwards, getting hotter and hotter, radiating X-rays and ultraviolet radiation and lots of other good stuff. But there's a second way that black holes can release energy, and that is through their spin. And to explain that, let me just give you, whoops, that seems to, what's happened there? There we go. That's right. Let's just make a cartoon. This is supposed to be a black hole, but it's red. So this is sort of depiction of the surface of the black hole called the event horizon, this imaginary surface, and then outside that is a region known as the ergosphere, and that ergosphere is characterized by, if you were there performing some surveying and not crossing the event horizon and going to this region here, you would have to spin around. The space-time required you to spin in the direction of motion of the spin of the black hole, the direction of rotation of the black hole. So inside this region, you would have to travel relative to your friends at a safe distance outside it. And this ergosphere has an amazing property that was first recognized by Roger Penrose, which is if you were in there and you had a rock, say, then you could take that rock and throw it into a black hole, and its total energy would be negative. So what that means is you've got a black hole, you've got something that you're creating in the ergosphere, throwing it into the black hole with negative energy and negative mass. So that means you're extracting energy. This is what we call in physics a thought experiment. It isn't the way that the universe does this. It doesn't have fourth-year students who are sent by their teachers who do this job for them. What it does instead is it finds slightly different ways of extracting this energy, but it says there is spin energy that's available, just like if I took a top and spun it on this table, it would slow down, energy would be released as that top slowed down. So there are two types of energy that can be released, and it's all just energy. One is gravitational energy, and the other is spin energy. So let's turn to those and how they're made manifest. Here's what was probably the first convincing demonstration that persuaded astronomers, who at that time were a little conservative, that black holes really did exist. This was a famous source of X-rays called Cygnus X1, and it is an example of a stellar mass black hole, or a stellar black hole. It has a mass comparable with that of a typical star, somewhat greater than that of the sun, but not a lot. And what happens is it has a companion, and that companion gives it gas which spirals around it, and that spirals in, releases its gravitational energy, and glows as X-rays. And through arguments that I won't rehearse here, it was discovered that it was too heavy to be a neutron star, therefore it had to be a black hole. There are other reasons, but that is essentially the most important one. Now, in fact, at the time when this happened, which is I think 1971, there was in fact quite a lot of evidence there were plenty of other black holes in the universe, but most astronomers had not really been persuaded of this until they saw this case. So this is an example of gravity power because most of the energy is released from this accretion disk. And so this, as I say, was the sort of culmination of this sort of three-stage argument. Not only black holes should exist and must exist, they actually do exist. And so the theory and the astronomy combined to produce an application. The second, I'm going to use just a cartoon here. This is a calculation, and there are many we've seen at this meeting. We've seen many much more sophisticated ones, but this suffices just to make the point that I want to make. I'm going to just maybe I have to do that. There we go. The movie, yes. So basically what we have here is a calculation of magnetic field that threads the event horizon of a black hole. So imagine magnetic field lines like those around the Earth, And these magnetic field lines are going into the surface of the spinning black hole, and they're taking energy away from it, taking away the spin energy of the black hole. This is a second mode of accretion. It's spin power, if you like, and it's the second thing that can happen in astronomy as a source of energy. If we go on to the observational story, this is the first quasar that was ever discovered by Martin Schmidt, shown here, in 1963, the same year that Kerr found his solution to the spinning black hole problem. And this was a massive black hole sitting in the middle of a distant galaxy. And this galaxy just looks like it was called quasi-stellar because it just looked like a star. Like that. That's what it looked like at that time. And I just want you to notice this feature, which I'm called a jet, which I'll come to in a moment. But this was a massive black hole, and it's the first one that was recognized as such. And these quasars were extraordinary because this simple, very tiny thing, smaller than the solar system, was more powerful than 1,000 galaxies, can be more powerful than 1,000 galaxies. That was quite a stunner for the astronomers, and then they realized there were quasars all over the place and slightly invariance on quasars, and we now believe that most galaxies, at least the massive ones, have black holes somewhat like this in their nuclei. This feature that's coming out of it, I called a jet, and this too is a very common thing. We see, I'm going to show this montage a few times because I'm going to give you some examples of this. This is just a very small part of the sky shown by a South African telescope, and you can count the number of these so-called active galactic nuclei. These are the galaxies with the black holes and the jets and so on in them. And there's about 1 billion over the sky. Here's another example of a jet. This should be well known to everyone here because in 1054 AD in Western counting system, there was an explosion, a supernova explosion that was seen by Chinese astronomers, and very few other people who should have seen it. There are perhaps a couple of other people who might have seen it, claimed. And that is called the Crab Nebula, and it's very well documented in Chinese history. And we now see it today in X-ray astronomy, and in optical, and in fact, the whole spectrum. And it has a neutron star in it, as I mentioned before, not a black hole, and it makes jets. Here is another neutron star that spins, was made by a recent supernova explosion, and it too makes jets. And what you'll see here, these lines here, are basically telling us that associated with these jets are very highly organized lines of magnetic field, like those around the Earth. You've seen pictures of bar magnets and the magnetic field around the Earth and so on. And in fact, in the solar wind and in the solar system, there are an organized magnetic field. The same is happening here. So this is very good evidence that the making of these jets is strongly associated with magnetic field. Here is another case. This is nothing to do with black holes. It is a star in formation, a so-called protostar. It too makes jets. The last four cases I'll return to later in this talk. So there's a very common mechanism for making jets, and what we believe is that the magnetic field associated with the spinning black holes and these disks of gas orbiting them, that magnetic field is creating these jets. So let me tell you a little bit more about black holes. Like human beings, they can put on weight. They grow. And we spent a lot of time at this conference discussing their diet. And there are as many opinions as there are popular books on how to control your diet. And so here is M87. Here's the image that you must have seen of the black hole shadow as imaged by this combination of radio telescopes called the Event Horizon Telescope. It has jets associated with this. Is seen as X-ray wavelengths, but we see it throughout the electromagnetic spectrum. It was first discovered by this man, Heber Curtis, in 1918. And the black hole was weighed by one of my colleagues, Walt Sargent, and he got almost exactly the right answer in 1979. And there's been lots of debate since then, but the current view is it's almost exactly the answer that he and his colleagues got at that time. This galaxy here, which is known as M87, with its black hole at its center here, is sitting in a giant cluster of about 1,000 galaxies called the Virgo cluster. We'll return to that point in a short while. But what's special, one of the other things that's special about this black hole is that it's very heavy. It is about 5 billion times the mass of the Sun. 5 billion times the mass of the Sun. It is very heavy. And we know of some that are probably 30 billion times the mass of the Sun. So these massive black holes have really put on a lot of weight. They have had a very uncontrolled diet. Here's the one in our galactic center. You saw this picture before of the stars that have been traced by infrared astronomers using, the astronomers aren't infrared, it's the astronomy they do is with the infrared wavelengths, and they use infrared telescopes because you can't see through all the dust and the mess, to the galactic center, and you trace the orbits, much like the ancients traced the orbits of the planets around the Sun. And we have a black hole there, but instead of 5 billion solar masses or 6 billion solar masses, we have 4 million solar masses, and that's the mass of the black hole in our galaxy. And it is rather a pathetic thing. It is dormant, it is starved of gas, and is nothing to be proud of at all. But do not feel ashamed. You wouldn't want to live next to a quasar. So we should be grateful that we live in such a near to such a starved black hole, and we've been able to trace this. I think I've got a little movie here. I don't know if this is coming up or not. Yeah, there we are. This is not a simulation. This is actual measurements made with telescopes and tracing the orbits of stars around the black hole. Okay, and so this has been going on. Two groups have been doing this for now nearly 40 years. And you can see very clearly that it has to be a central mass with a black hole. There is another way the black hole's diet can be addressed, and that is they can be fed. They can be very hungry. And when they're very hungry, they can eat whole stars. And Professor Dye, who organized this meeting, is an expert on this. And these are called tidal disruption events. And basically what happened is that a star gets too close to a black hole and is ripped apart by the gravitational field there. And then it makes a lot of debris, which we can then observe. So I think there should be a movie here. And this is a picture of what you would see with a black hole, like in Interstellar and so on. And then in a short while, you'll see a star come into this, orbit the black hole, unsuspecting, like Icarus in the Greek myth, and it is then going to go around the black hole, in a different perspective here, and it is going to be ripped apart. This is what it looks like in the star. There's a star, it gets like huge tides there, and then watch what happens now. All this gas gets flung out and then makes a sort of disk around the black hole. This is called a tidal disruption event, and you'll see there's a jet there. They can sometimes make jets. This one here is an observation of one of those jets in a tidal disruption event. Black holes can cry when they are born. How are they born? Well, one of the ways is in a supernova explosion. When a massive star runs out of nuclear fuel to hold it up against the pull of gravity, then it will collapse. And under some circumstances, in some mass range, it will make a black hole. And when it does this, in a minority of cases that we don't fully understand, it will create a structure called a gamma ray burst. Here's a supernova explosion. This is a depiction of what happened in the nearby galaxy, the Large Magellanic Cloud, 1979. So that's before and that's after. There's a huge supernova explosion, and a good supernova explosion can outshine the whole galaxy. And in that case, in case of supernova explosions like that, it can leave behind a black hole in some cases, and it also leaves spectacular displays. This is an image of what happens after the supernova explosion. But in this minority of cases where there's a gamma ray burst, what happens is the black hole forms. There is a disk of gas in the center of the collapsing star, and there are two jets that are made, and those jets are so powerful they punch their way out of the collapsing star, making a gamma ray burst. And these are seen by firstly gamma ray astronomers, so going back to the 1960s, and now by everyone else. And this is one of the prime ways of making these gamma ray bursts, and we see them especially when those jets are pointed towards us. There's another way we can make black holes, and they cry too. This is if you have two neutron stars in orbit about each other, and this is a cartoon of two neutron stars in orbit around each other, and these neutron stars, called pulsars, send out pulses of radio waves, and these have been known, the so-called pulsars, as binaries, they have been known since the 1970s, and by measuring them, you can see them radiating waves of gravity called gravitational radiation, and that causes their orbits to shrink. The one that was first discovered, you have to wait 20 million years before it is going to shrink completely. But this one, but with the advent of gravitational wave astronomy, using the LIGO Observatory and other Virgo Observatory and other ones, then you get, in this case, two neutron stars. You can actually observe them merging, obviously different pairs of neutron stars merging. So here's a simulation of that, and then at the bottom you can see the gravitational waveform they produced. And that is what is measured and seen quite regularly. We know now many examples of merging neutron stars that have been measured by gravitational radiation telescopes. And they too have their birth cries. You see them in gamma rays. You see them make bursts of gamma rays. You see them as well throughout the electric spectrum, and you can also see them make jets. So here's one of those newly formed black holes by a pair of neutron stars, and that actually made a pair of jets, which was seen there. So we observe those too. And it's the same, probably, extraction of rotational energy by magnetic field that's going on in that case too. I said they are social, as well as anthropoid, and often they find dance partners. So the black holes themselves can exist in binaries. Here are two massive black holes in a nearby galaxy, and they both make jets. So we have two pairs of jets made by two orbiting black holes in a galaxy. Here's another example, which is a sort of cartoon here. This is a recent one that was discovered, and it was, this is not completely demonstrated to be a case of an orbiting black hole, but it's certainly a compelling explanation. It's a black hole, one black hole here that's making jets. And these jets, they're pointed towards us, and that's what the feature that makes them very bright when they're pointed. Don't get paranoid. When they're pointed at you, they're very bright. It's just Einstein's special relativity. And what was seen here was a coherent periodicity here. And in this case, the explanation that was advanced is that we've got two black holes in orbit about each other, and as the black hole making a jet pointing towards you is going around like this, it's orbiting, then you get a variation in the radio emission that this black hole makes from the jet, and that produces about a 5-year period, and that produces a black hole, that's a black hole binary, and if you wait around for 10,000 years, then you will see it merge. That's the story, and about that. Here's another example of one of these cosmic dances. This involves a stellar black hole. This is called SS433. It's a rather forgettable name, and it's one of these cases where you've got a star and a black hole and a disk orbiting that black hole, and it makes the jets. Here's the black hole. See, there's two jets, and those jets are observed to do that. They're observed to what we call precess. They're observed to change their direction. And we observe this very well, and there are several explanations for what's going on here, none of which are correct, and this has been known about since 1979, so if anybody here has a good idea, keep me off. They're relativistic jets, and they are spiraling. So these are observations. Okay, you can see these things. You can see the direction changing sky. And we learn a lot about them with our telescopes. And as I say, this is an example of a jet made by a disk and a spinning black hole in a nearby stellar object. Here's probably the most famous case, the first gravitational radiation detection of two merging black holes. This, I hasten to say, is a simulation of what a background star field would look like around these black holes. I hope there it is. So these are two orbiting together, and it's some sort of devil's dance here, and it gets faster and faster and faster. And then eventually those two black holes merge. This simulation fits the data of it, like that. And then what happens, it wobbles around a little bit, then just settles down to make a bigger black hole. Bigger black hole, thank you, sorry, I've not been using the microphone. You should have reminded me, I told you I was not good at microphones. And here's the data that was used to pick up that picture. I want to finish off by emphasizing what is probably one of the frontiers. These big black holes, particularly the ones in distant galaxies, and the jets that they make are credible sources for the highest energy gamma rays and neutrinos and cosmic rays, which I mentioned at the start of this lecture. It's not completely demonstrated. This is one of the exciting things, to find out whether or not this is the case. but they have all the necessary ingredients. Remember I said there was magnetic field and there was spin. And those of you who have done a little bit of electromagnetism will know that if we have something, a conductor like a black hole spinning in a magnetic field, it will create a voltage. And a voltage is not one of those flashlight batteries you have, which might be 1 or 1.5 volts. It is, in scientific language, as much as 10 to the 21 volts. In fact, it can be even more than that. It is 1 billion trillion volts. Okay, so this is very, very energetic. And something like this famous radio source called Cygnus A, which is a galaxy with a black hole no bigger than the solar system in its center, creating 2 jets, going way outside the galaxy, has the capability to make the highest energy neutrinos, the highest energy gamma rays, and the highest energy cosmic rays. Anybody here play tennis? Nobody play tennis? Anybody play football? Okay, so yeah, somebody plays tennis. Okay, good. If you hit a tennis ball hard, it would have the same energy as one of these most energetic cosmic rays, but that is just an atomic nucleus that has the energy of a well-hit tennis ball. So this is one of the big frontiers, is to understand if this really is the source of these very high energy particles. There are other ones, and that's one of the things we're discussing at this meeting. So here, what was I going to say? This is this one up here. This is one of those, a similar sort of radio source, radio jet, like Cygnus A, not quite as powerful. And this has been claimed, not terribly convincingly as yet, to be a neutrino source. And this is an important thing to say, is that there's scientific evidence that it is a neutrino source, and it is, but it's far from compelling. But what I think is compelling is that we're on threshold of doing neutrino astronomy. So this is an exciting time. This is science happening as we speak. Final thing I'll say is that these black holes, like human beings, have a large environmental impact. This is a cluster of galaxies. This is the X-ray emission from a cluster of galaxies, like the one around the M87 black hole and galaxy, but in a galaxy called Perseus. The observer who did this is in the audience, my friend Andy Fabian. It's not a leftover from Halloween. It really is an X-ray observation. And what you can see are the relics of old radio jets and sources. And another thing we've been discussing at the meeting is how those active galactic nuclei are moderating the environment around them in quite complicated ways and causing stars to form, new galaxies to form, suppressing the growth of galaxies, and so on. They have an enormous environmental impact. It is not passive. It is quite active. They have a very large role to play in the universe. There we go. And so in some sense, galaxies would end up, and black holes would end up much more massive if they didn't have this effect on their environment. So the environment sort of brings me back to our environment. And this is something to say to the young people here. It will not have escaped your attention that we live in a world of change, a world where there are challenges associated with energy and climate change and many other things that go along with that. This is a picture that was taken of the people at this meeting. These are astronomers, and the one you should observe 2 takeaway messages from this. The first is that this community is young, and the second is that it is global. There are people demonstrably from all around the world. That is the world of science. That is the world in which we live. And that is not a bad match to the challenges that face us all. And you might like to think about that a little bit. There are telescopes. One of the reasons why it is such a global business in astronomy, but in other parts of physics, is that these telescopes, like those that made the Event Horizon image, they're all around the world. They've all got to work together, like people have got to work together. And so here are some telescopes that have to work together. This one is in Chile. This one is Event Horizon telescope all around the world. This one is out in space. This is an X-ray telescope in space, and so on. There's so much happening that that there are big opportunities still in astrophysics, but in other areas of science. And so there's much out there still to be discovered. This isn't a book that's finished. It's a book that's only partially written. China is playing an enormous role here. Here are some of the Chinese telescopes. Some of them are real, existing, acting now. Some of them are proposed. It's a very exciting program. It's got neutrinos. It's got gamma rays here. That's right there in Lasso, which I visited, and the lead of that project is here in the audience. There's the fast radio telescope you may have heard of. Here's neutrino detectors, optical telescopes, X-ray telescopes. It's all there. So again, there's exciting possibilities for more discoveries and for learning about how black holes and much else besides operate in the cosmos. So in this talk, what I hope I have persuaded you of is that black holes are fascinating. They illustrate an awful lot of basic physics. They're real, they're alive, and they thrive, and they survive. So let's wish that for ourselves as well. Thank you very much indeed.
Okay. Thank you very much, Professor Blandford, for this very interesting, very inspiring talk. So now it's a Q&A session. So yeah, I would like to invite questions from the audience. Okay, please.
Hi. Hi. It's an honor to be able to ask a question. And as you've mentioned in your talk, an equation named G equals 8 pi t, and it's a rather simplified version, but you mentioned that T represents stuff, which includes bodies with mass and as well as radiation. But as G represents the curvature of space-time, and what I've heard of is that only mass can distort space-time, but you mentioned radiation also. So how can radiation distort space-time and cause curvature too? Thank you.
That's a very good question. And I'm sure that if Isaac Newton were here, he would have asked the same question. So very perceptive. It's perhaps within our experience that the Earth would attract an apple. So that's two massive things, or the moon, or a rocket. Okay, so that's something that's within our experience. But if we have a lot of radiation too, remember that E equals mc squared, and radiation has energy. All right, the light from that fluorescent tube up there is carrying energy. So there's energy there. And although it doesn't have a mass in the same sort of sense that you and I have, it has that energy allows it to provide a a contribution to gravity, which in Newton's language would be a form of like a form equivalent to mass, which is providing a force, but instead in Einstein's language, which is the one we have to use for cosmology and so on, and for black holes, it contributes to creating the curvature of space-time. So the radiation in the universe, particularly the early universe, curves space-time then. Okay, so it really is the same. And think about the equivalence between energy and mass, and that gives you a clue as to why radiation can contribute. And it's not just radiation, it's the neutrinos as well. They do it as well. Thank you for a nice question.
More questions? Yes, please.
Testing. So I wonder, like, what happened to the matters when a planet collapse, like, become a black hole? So where does the matter goes? Like, dark matter, like, do the stuff?
Oh, again, a very nice question. A planet probably is unlikely to collapse to make a black hole. You need something more massive than that. A heavier star, for example, when it's run out of nuclear fuel, can collapse to make a black hole. Now, you might say, well, is it choosy? Does it only eat certain things like hapless astronauts or gas or something like that? And the answer is no, it eats everything. And even dark matter it will eat. Even your household refuse it will eat. So even the radiation from over there it will eat. Okay? So and as it eats, it will grow in mass. So yes, it is indiscriminate, it will eat everything. Omnivorous.
Yes, please.
Hi, Professor Blanford. We meet again. It's an honor to actually see you in real life, other than in last year. So I have a question regarding the binary black holes and the jets that it emits. So you've mentioned that black holes have spin energy and gravitational energy. So how does the spin energy affect the jets that in binary black holes, and how does it cause it? Is it possible that it causes it to wobble? Thank you very much.
By binary black holes, do you mean the ones that are observed by LIGO?
Yes, yes.
Oh, okay. That is, again, an excellent question. You may recall that I showed a picture of the gravitational waves that were measured by LIGO from the first black hole binary. The details of those waves depend on the spins of the black holes. There are two black holes there. Each of them has a spin. And the details of the waves that you will get will tell you the spins of the black holes. In practice, it's been a bit hard. The measurements aren't quite good enough to be sure what the spins were in black hole binaries like that. But we're working on it, and we're getting part of the answers in, but it's a work in progress. I suspect it will get better over the next few years, that we will have a clear understanding of the spins. So yes, the spins are definitely important. And what is, I think, inevitable is that any of these coalescences, even if you start off with two black holes that are not spinning at all, the one that's left at the end, which has less mass than the mass of the two black holes that combined, that merged to give it, because the rest of the E equals mc squared energy went off in gravitational waves. In the case of the first one that was discovered, it was 65 solar masses, became 62 solar masses, and the 3 solar masses went off in waves. So that black hole that's left over must be spinning. So we make spinning black holes, and it looks like a large fraction of the spinning black holes in the nuclei of galaxies and in the stellar black holes as well, where we've been able to make determinations, and people in this room have been doing that work, seem to be spinning very rapidly.
Yes, please.
Hello, Professor Blanford. I would like to ask, maybe it's silly, what will happen if all black holes disappeared? Are there influence to our lives?
If all black holes disappeared,
Yes.
I think I would be out of a job. You would fire me. There is always. You failed to answer a silly question. You actually asked a perceptive question, but let me change it slightly. If we have tiny black holes, one's no bigger than a mountain, then as Stephen Hawking, who I showed a picture of, first demonstrated, they can actually disappear over the lifetime of the universe, or even shorter. They can radiate like a star, and so they're losing energy. And guess what? E equals mc squared, so they're losing mass. And eventually, there will be left nothing. Well, we're not quite sure what is left, but there's essentially nothing left at the end of this. And so those tiny black holes, if they exist, will disappear completely. The trouble is we're not sure they exist, and several of us have been sort of engaged perhaps a little bit in looking for them, and we failed miserably to find them. And if I wear my hat as a theoretical physicist, I would say it's awfully hard to imagine how the universe made them in the first place. The ones inside active galactic nuclei and in binary star systems, those you could easily, people did expect them to be made at some level, but to make these very tiny black holes, I lack the imagination to know how that could have happened. But as often happens in astronomy, nature is clever than astronomers. Not that they'd like to admit that.
Thank you, Professor Blanford, for the nice talk. I want to ask you a question. So, seems so from your talk, significant of your career is studying the black hole. I have a question that I wonder, when do you start to decide to have this romance with black holes?
Romance with a black hole, yes. Okay. No, I just fell into it. What can I say? Okay. But the personal history was, as a child, I used to go to the public library, and there was a section there for children's library, and there were books on astronomy. And so I read about books on astronomy. So that was how I got into that business. Then when I was a teenager, I didn't really pay much attention to it. And then when I was an undergraduate, the very first talk I heard, first talk I ever heard about astronomy, first time, was one given by the discoverer of pulsars, neutron stars, and I was exceedingly impressed by it, I have to say. And of course, that turned out to be a very big discovery. But still, I was originally a chemist, and then I became a physicist, and I didn't expect to do astronomy, but then at that time it was very exciting, and I had a charismatic advisor who, after listening to him for half an hour, said, "This is what I want to do." And then I started working on very different things. And then one thing led to another, and I got interested in the jets and so on. We weren't quite sure what was making them, but after a while, I and many others became convinced that it was black holes that were doing the job, and that's really what happened. I sort of followed the observational evidence, which led to black holes rather than I wanted to do black holes. It was really following observational evidence, I think, that led me there. And so that's my life story. There you go.
Thank you for giving the great lecture. What exactly are these jets made of? Like what type of particles?
Probably many things. It's something we haven't really discussed at this meeting yet, but it will be discussed in the next couple of days. So I'll give you my answer to that question. And my colleagues here will probably disagree with some of what I have to say. And that's part, I want to emphasize this, that is part of the essence of science. This is understanding in progress. And you may come back at this in 5 years' time and he said that. Okay? But I'll give you my answer as of today. The big jets that you see made by black holes, not the other ones, but the ones made by black holes, are made by electric magnetic fields. We call that electromagnetic field. And they're powered by the rotation of the black hole. That means that what they start off with is electric field and magnetic field. And that's essentially all of it. But as they go out, they go through a bad neighborhood, the nucleus of a galaxy. And there's a lot of gas there, and there's stars, and there's other stuff around, all the detritus from the evolution of the galaxy. And it sort of drags it into the jet. And that means the jet also contains a lot of gas as well. That's going along. It may still be moving at the speed of, almost the speed of light, but it's got a lot of gas there too. And the further along it goes, the more gas it picks up. So that by the time it gets to the end of the jet, there's a lot of gas there as well, and as well as magnetic field and cosmic rays and lots of radiation and all that good stuff. It's all in there. And so it's more of a mixture by the end. But I personally believe most of these jets start off in essentially a purely electric and magnetic field. There are electrical currents there and so on, but that's not part of the composition. It's just electric and magnetic fields. That's how they start. And then they become more and more contaminated with more and more stuff that they've picked up. They start the day clean, and they're pretty dirty by the time the evening comes. Okay.
Yes. Good evening. Good evening, Mr. Blanford. I'm Isaac, Kara study, and she's 6 years old, and this girl. And so I have. Do you have some advices for me, or for the older little children, as how to start to explore the knives of black hole? Or like other science. Thank you.
There are many nice books out there written about black holes. Most of them are out of date because there's so much being discovered, but they're still very much worth reading. And I would say if you prefer books, then there's my colleague Kip Thorne wrote one that's now quite old called Black Holes and Time Warps. That's actually very carefully written for describing the physics of black holes and well worth reading. It's out of date as far as the observations are concerned, but the physics has not changed, and that is good. And if you really fancy wormholes, that's the place to go. So that's one thing. And if you want something a bit more modern that's very short and written at a much simpler level, another of my colleagues, Catherine Blundell, has written a nice, very short monograph that you can find. I think there's an audio version even on you can find that through the web and so on. So, Blundell.
Yes, please.
Professor, there's an assumption that there's a singularity inside the black hole, right?
Yes, we think there's a singularity inside the black hole. There are other ones. One, for example, in the early universe is another place. But the black hole is what we're interested in here, yes.
So today, what's the best theory to explain this, or whether we can explain this now? Explain the physical phenomena of singularity.
The best theory.
Best theory, any theory to...
Well, anything called quantum gravity or string theory is in some sense dealing with that problem and much else besides. So, and those are works in progress. Immensely intelligent theoretical physicists have devoted their lives to this problem. They've understood a lot, but they still don't have a working theory in the sense that Einstein's theory of relativity is a working theory of classical gravity at the big scale, what we call the classical scale, a big scale. And so that works. And I didn't emphasize this point, but there are tests of general relativity at the level of 10 parts per million, which are serious tests that it could so easily fail, and it has passed every one of them. So it is, that's the reason why now we have quite a lot of confidence that it's a good theory of gravity. Maybe there's some little wrinkle or something to it, but at the moment it seems to be working extraordinarily well. It's been tested in so many different ways, and it's always seemed to come in right on the money.
Hi, Professor. Thank you for the wonderful talk. This is a question I probably should know the answer to, but I don't. I wanted to ask if black holes have infinite gravity and nothing can escape them, how is it that we see these jets being emitted from these black holes?
That's, again, well, obviously a very good question. And basically what happens, it's a little bit like, remember I mentioned this thought experiment of Roger Penrose, of orbiting and throwing something into the black hole. Well, what that says is, if you orbit with the black hole and you ask what the energy of the rock is, it is positive. But if you look at that from another frame of reference that is not orbiting with the black hole, the energy is negative. And that's why the energy that you associate with having been thrown into the black hole is negative, because it's that energy in the other frame of reference that's conserved. So we say that we have extracted energy into the black hole, from the black hole, by throwing negative energy into it. The same thing happens with the electromagnetic field. If we orbit with the black hole, then we will see energy going into the black hole, as you would expect. But if we stand outside in a frame of reference that's not orbiting, and that is the frame in which energy is conserved, that frame in which energy is conserved, then we see energy coming out of the black hole. And that's the way it works. So it's an accountancy trick. And you don't go to jail for it.
Yes, please.
Yes, I would like to know what do you think about the black holes, the relation between black holes and dark matters of our universe?
Again, a very good question. Some of my colleagues over the years have said that dark matter is just a lot of black holes. That's as dark as you can get. Let's just use those. In principle, that was once possibly the case. Now I think not. We have observational and experimental limits that make that very difficult to sustain in a credible way, especially for the bigger black holes. So there was a time when people took that relatively seriously. So whatever dark matter is, we're now looking at other candidates. And astronomers and physicists who have both gotten in the act have done an extraordinarily good job in failing to solve the problem. And I mean that in full admiration, because they have produced limits on the candidates for dark matter that are orders of magnitude greater than even they promised when they started their observations and their experiments. So we know what it isn't. And we still have some candidates out there, and people are hard at work with various clever techniques, seeing if they can detect the nature of dark matter. But it's one of the biggest and most exciting problems in physical science, in my view.
That's what I mean is, if dark holes contribute a lot of the massive things for those dark matters, that means the black holes, would that be a great portion of the dark holes, so they contribute the masses for the dark matters?
So I couldn't quite get, there's a word,
That means, if we add up all those masses of the black holes,
yes,
would that be almost equivalent to those dark matters, or how many percent about it?
Okay, the ones we know about are only a tiny fraction of the regular matter in the universe, let alone the dark matter. They're only a tiny fraction. So the answer is the ones we know about are not what's the dark matter that which we see in controvertible evidence that it's out there. So, but so we need a better idea.
You mentioned that energy to curve the space-time. So does that mean that it's possible to exist maybe a massless black hole that's merely made of some energy?
A black hole that?
Massless black hole.
A massless black hole.
That's simply made out of energy.
Oh, in principle you could do that. In principle, and this is a thought experiment. A thought experiment, if I had lots of beams of light and I shone them all at the same point, at the same time, from the same distance, in principle, I could create a black hole out of radiation. But it would have mass. Because E equals mc squared. Light has energy, and so there's an equivalence there. And so what if it made an event horizon, which in principle it could do, then it would make a black hole. In practice, of course, this is only a thought experiment, and like many of these thought experiments, don't try this at home.
So we have time for the last question.
Oh, last question. No,
yeah.
Okay. I get the honor. I guess this is kind of a silly question, but maybe a couple months ago, I made a bet with my former supervisor regarding primordial black holes,
yes,
or very small black holes. I bet that we will detect them within 20 years' time. He bets the opposite one. He argues that primordial black holes are way too weak to be found by gravitational waves, because I work on gravitational waves.
Yes.
But my question is, do you think there are any other ways, maybe jets, accretion disk, etc., that are more promising to be found by, are more promising to find such black holes?
Well, one of the things that was tried in the 1970s was, and it was based on a now essentially discredited view of particle physics, was that when they got small enough, they would explode. And then the best way to find them was through the radio flashes that they made. And we've seen lots of radio flashes. However, these are not exploding black holes. And we now know that that's not a really credible explanation. I think, for me, I mean, I'd love to be wrong about this, but I lack the imagination to know how to make them, even in a cosmological context. And cosmologically is the best place to make them. But, you know, what I think, or any of my colleagues think, is not, you know, is not what's important. What's important is to go out and look for these things. And maybe the gamma rays are one of the ways you may find these. Maybe even direct detection could happen. That could even happen. But I think it's, you know, it's one of the exciting things is that, you know, plenty of people said neutron stars and lots of people said neutron stars and black holes, they don't exist there. They're just sort of silly physicists' imaginations. And they're abundant. There are 1 billion neutron stars in our galaxy alone, and probably 10 million black holes in our galaxy alone. So they're common, you know. And so, you know, we could easily be wrong there. I hope we are, but I feel we're not. So I'm a reluctant conservative. Okay.
All right. So yeah, I know there are many more questions from the audience, but for the interest of time, so we need to end the event now. Yeah, so let's give Professor Blanford another view.
Thanks to all of you for the wonderful questions. I really, they've been great. Thank you very much indeed, and for all your hospitality here.